And we're back here in the Simpkins Physics Closet for another episode today. It's the VT Graphs recap. So, velocity time graphs, right? We've been talking about free-falling things, and if something falls freely, that means only the force of gravity is acting upon it. If you were to graph a velocity versus time graph for something that you just drop, let's think about it. Before you let it go, zero velocity, so it would start like this. After you let it go, what's going to happen? It's going to increase velocity in the negative direction. So a little bit of negative velocity, a little bit more negative velocity, a little bit more negative velocity. And if we graph that, it's going to be a straight line whose slope is going to be, how much you know that, Mr. Simpkins? Well, the slope is rise over run on a VT graph, change in velocity over time. And the change in velocity is, over time, is acceleration. And when you drop something, now we all know, after talking about free fall and hang time for a whole week, the acceleration due to gravity when you drop something is 9.8 meters per second squared. And that's what the slope would be of a velocity time graph for something that you just drop. What about something that you just toss up into the air? I'm going to actually go back and do this on this slide. What about something you toss up into the air? What would the VT graph look like? Well, if I chucked it up into the air, it would start with a positive velocity. And on its way up, it would be slowing down until it reached zero velocity at its peak. And then it would come back down and actually would hit the ground at the same speed if it was at the same height. And that would be a negative velocity. And so that would also be a straight line whose slope is, you guessed it, negative 9.8 meters per second squared. So we've been trying to tie together velocity time graphs and gravity here in the last little bit. Let me erase this and clean this up and give you a quick recap of why these VT graphs are so magical, all the things that we can find from them. And then you're going to do some practice today on that fourth page of your packet for this week that emphasizes some of these VT ideas. So here's our first one. All right, we got a VT graph. It says, the diagram shows a velocity time graph describing the motion of the car. Describe the motion of the car during these certain times. All right, so you know what? It'd actually be better if I'm not in presentation mode for this and get rid of that guy. Let me just type her in here real quick. And let's talk about. So from part A to B, let's take a look at what's happening. From part A to B, we see that our velocity starts over here as 0, and then our velocity is steadily increasing until it gets to 10. All right, so if I had to describe that, I could use a couple of descriptive terms for that. I could say we start from rest and increase to a velocity of 10 meters per second. Now, how long did it take us to do that? 5 seconds. Change in velocity is 10. Over the time it took to do that is 5. 10 divided by 5 is 2. What's that mean? That means our acceleration. Our acceleration is 2 meters per second squared for that segment. How did I know that? I did the slope. Rise of 10 over run of 7. All right, look for part BC. What happens in part BC? Part BC, we're looking at a steady velocity. Now, don't be confused. I know you love your XT graphs. This is not a position time graph. This is a velocity time graph. This shows a steady velocity of 10. Some people, not you, of course, some people be like, well, you're at rest because it's a flat line. No. That would be for a position time graph. This is a velocity time graph. And on a velocity time graph, if we have a line that is horizontal, that just means that our velocity is steady. It's not changing. So we could say we have a steady velocity of 10 meters per second for the next 10 seconds. Right? We went from the time of 5 to a time of 15. Not too bad. And then from C to D, all right, well, it looks like we slow down at a rate of, rate, that means the change in velocity over time, which for this graph is the slope. So what's the rise, or in this case, the drop over run? Well, it would be negative 10 divided by 5, or just negative 2, the slope there. The rate of our acceleration would be, it would be negative 2 meters per second squared. Okay, so not so bad. What distance is covered in the first 5 seconds? Here's where things get interesting. All right, so let's get to our draw tool. Let's blow this up a little bit so we can see a little bigger. What distance did we cover? Well, remember, to get distance from a velocity versus time graph, velocity is displacement over time, and so that means displacement is velocity times time. Velocity times time. You mean like 1/2 base times height? Look. The height is the velocity, and the base is, sorry, the base is the time. There's v times t. Oh, that gets me x. So remember this strategy we did last week. The bounded area of a VT graph solves for the displacement. And here's why. Because displacement is velocity times time. So what distance did we cover in the first 5 seconds? So we did 1/2. The base is 5 seconds. And the height is 10 meters per second. And so that's going to be 50, and half of 50 is 25 meters. So that's how far we went in the first 5 seconds. What was the acceleration during that time? Well, remember, if bounded area gets you distance, then the acceleration is found by doing the slope. And funny, I already spoiled this one because we already did that. So the slope is 2 meters per second squared. Now, the last part here is very tricky. It says, calculate the total distance covered by the car for all 20 seconds. Okay, it's actually not that bad. We already know that we covered 25 meters for the first 5 seconds. Well, since the bounded area, I'll make some marks like this, since the bounded area, the area under the VT graph here, is the displacement, if I calculate this shape, look, the shape has a length of 10 from 5 to 15, and a height of 10, and a 10 by 10 would be a 100. 10 times 10 is 100 meters. We cover 100 meters from 5 to 15 seconds. And then from C to D, we have another triangle here, and actually that triangle has the same area as the other one, 1/2 base times height. And so what do we see? After 20 seconds, we went 25, then we went another 100, then we went another 25. So what's the total? Our total distance there is 150 meters. That's how far you're going to travel on that VT graph. Now, 2 big things before I let you off to the practice. The practice looks like this. It's kind of hard, so let me give you a tip. What about negative motion? All right, look at this velocity graph. We've discussed some graphs like this. Look at this one. The velocity here is -5, and then -2.5 if I had to estimate, and then 0. So that graph, if I do the bounded area down here, that's actually going backwards. So let me show you what that would look like. It would be 1/2, consider, the base is 4 seconds, but the height, we'll call it like this, the height is -5 meters per second. Just throw the negative in there, because what that'll do is it'll remind you that we traveled backwards 10 meters for the first 4 seconds. Now, if I said, what was your displacement for 4 seconds? Displacement does include direction. So you would say the displacement is -10 meters. But if I ask you what distance did you cover, remember distance is a scalar, which means it does not have direction. So the distance there would be 10 meters. So I want you to keep this idea in mind as you do this whole chart. Let me give you a couple pointers. Here's your chart. You're going to first, it says sketch the shapes and calculate their bounded areas. Remember, you can break this into simpler shapes. All right. Just be mindful here that you're going to be doing a calculation for negative displacement here and here. Those other ones will all be positive. So here are some things to consider. Are you moving to the left or to the right? Well, remember, on a VT graph, if you have any values down here, negative velocities, you're moving to the left because negative velocities would be moving to the left. And if you have any positive values, you'd be moving to the right because positive values on a VT graph mean that you're moving to the right. So when it says moving right or left, you just check that out. Now, of course, some of them might be neither, or you might be not moving at all. For acceleration, just a little reminder, you're going to calculate the slope for each of those little segments using 2 points, rise over run. And for speeding up or slowing down, we had some great conversations about this in class. Remember for this one, all right, remember for this one, you are slowing down as you get closer to 0. So those would look like slowing down. But you are speeding up when you're getting further away from 0. So with that little picture, I hope that brings back some memories from last week and you can answer those questions. Finally, down here, when it says what's the distance traveled for the entire trip, and then it asks you for the speed, remember that speed is distance over time. And remember what I just said before. Even if you have a negative value there, the displacement is going to be negative, right? But the distance is going to be positive because distance doesn't include direction. It includes every step, whether we went forward or backwards. So keep that in mind. Then when it says what's the object's total displacement, well, if you have some, you're going to have 1, 2, 3 positive values from that stuff above the VT graph, but then you're going to have 2 negative values from the part that happened below the x-axis on the VT graph. So make sure you're adding and subtracting appropriately, and then with velocity you do delta x over t. All right. So that is your activity for today. I actually want to get this sheet from you guys. All right. So you can take a look there. I want you to submit your work for today for the VT graph to that assignment. And this is just a nice little overview of our velocity time graph strategies. All right. So I'll see you next time. Until then, it's Mr. Simpkins in the Simpkins Physics corner.